So previously you have seen how to express the Maxwell's equations in integral form. Now we want to express them in differential forms. And for that we have to understand some basic concepts of vector calculus like the Gauss theorem and Stokes theorem. So let's begin. So in order to understand the Maxwell equations in differential form, we have to know some basics of vector algebra. Now you are already familiar with this delta operator, right? This delta operator, when it acts on a scalar field, gives the gradient of that scalar field. So if we apply this delta operator on electric potential phi, then we get this quantity. But you know that the special derivative of electric potential is electric field with a minus sign. So when we take the partial derivative of electric potential with respect to x, we get the x component of the electric field with a minus sign. So combinedly, these three components give us the electric field E. Now if you look carefully, you will see that the electric potential was a scalar function, and when we applied operator delta on it, we got a vector quantity, which is the electric field. So we can say that when delta acts on a scalar field, it gives a vector field. Now this delta operator can act in two ways when applied on a vector field. We can extract a scalar quantity from a vector field if we apply delta as a dot product. We can also extract a vector quantity if we apply delta on a vector field as a cross product. This scalar quantity is known as the divergence of the vector field on which it is acting. And this vector quantity is known as the curl of the vector field on which this operator is acting. Now we want to understand an important theorem in vector calculus, which is known as Gauss's theorem. For that, we have to understand the concept of flux. Say for instance, we have a vector field like this. Then if we have a mathematical surface like this, the quantity flux of that vector field is defined as the surface integral of that vector field over that whole surface. Now if this vector field is an electric field, then this phi will be electric flux. Now you can see that this flux is a scalar quantity. So if we consider two mathematical surfaces like this, then the total flux would be simply the summation of these two flux. Now say that we divide this mathematical surface in two parts like this. This portion we can call SA and this one to be SB. And this is the common surface. Now we can define this whole closed surface into two closed surfaces S1 and S2, where S1 has this face SA plus this SAB, and S2 has the face SB and SAB. Now the total flux to this closed surface S should be simply the summation of the flux to the closed surface S1 and the flux to the closed surface S2. So phi S will be equal to phi S1 plus phi S2. Now what happens if we divide this whole closed surface in many infinitesimal closed surfaces? This simple idea will lead us to the Gauss's theorem. Now in order to understand the Gauss's theorem, let us consider an infinitesimal cube through which a vector field E is passing through. Say the vector field has E1, E2 and E3 components along X, Y and Z direction. Also, let's say that this infinitesimally small cube has dimensions delta X, delta Y and delta Z in those three directions respectively. then the volume of this cube will be simply delta x times delta y times delta z. Now we want to find out the flux of the vector field E through this small cube. We know that a cube has 6 faces. So the total flux through this cube would be a summation of fluxes through all 6 surfaces. So let's calculate these fluxes one by one. Now what would be the value of the flux phi1, which is the flux through the surface 1? Now let's say the coordinate of this point is x, y, z. Now to calculate the flux through this surface 1, we need to find out the electric field which is passing perpendicularly through this surface. And the perpendicular direction to the surface is this x direction. So the component of the electric field which will pass normally to the surface will be E1, which we'll have to evaluate at this point x. So phi1 is equal to E1x times the area of that surface 1, which is delta y times delta z. And we also have a minus sign here because the electric field is entering through the surface, not going out. Similarly, we can calculate the flux phi2 through this surface too. Here also, the electric field passing normally to the surface is E1. But the coordinate of this surface is now x plus delta x. The area of this surface is still delta y times delta z. And there is no minus sign here because the electric field is going outward from this surface. So to find out phi1 plus phi2, we can simply add these two terms and take delta y and delta z common. And this is just the change of component of electric field in x direction, which we can rewrite as the special rate of change of electric field in this direction times the special change, which is delta x in this case. So for the two surfaces perpendicular to this x direction, we got that the summation of flux is equal to the special rate of change of the electric field in that direction times the volume of the element. Now we can actually predict the change in flux in other two directions as well. So in the y direction, it should be partial ddy of E2 times the volume element. And in z direction, it should be partial ddz of E3 and times the volume element. And for the total flux, you just have to add fluxes in all three directions. Now we can take the volume element common and then see that the remaining part is the divergence of the vector field E. So the total flux through this infinitesimal cube is the divergence of the vector field times the volume of this cube. Now in case of any random shape and size of volume like this, we can actually divide that volume into many infinitesimal cubes, right? Then the total flux through this volume should be the sum of all the fluxes through these infinitesimally small cubes. And we can write down these fluxes as the divergence of the electric field in that volume times the volume of that cube. Now to find out the total flux accurately, we have to extend this sum for infinite number of cubes. And in that limit, we can rewrite this summation term as an volume integral of this divergence term. So we can set this thing to be equal to this definition of flux inside this volume. And this is what we call the Gauss's theorem, where S is any mathematically closed surface and V is the volume inside that surface.